Hey Reed, you sent me a message about some problems you were having working on motor banks in code. And so I want to go through an example of a motor bank just to help you see what happens when we do calculations for them. One thing I want to point out too is that the PowerPoint for motor banks shows a motor bank with lots of calculations to do. Like I think it'll show a motor bank and then ask you to figure out the conductor size for each individual motor, overload size for each individual motor, overcurrent size for each individual motor, and then it will go over sizing feeder conductor size and feeder overcurrent device. So in that PowerPoint for motor banks, they're just giving you a bunch more practice for individual motor calculations as well. So keep that in mind when you're looking at that. And if you need to, go back to individual motors and take a look again at how the PowerPoint for individual motors goes through each of those individual calculations for overloads, for conductor size, for motor, for overcurrent size, that kind of thing. All right, when you're doing a motor bank, there's really only two calculations that you do that are different than what you would do for individual motors. One is conductor size for the feeder conductor for that motor bank. And a question I often ask students is, when you're looking at this diagram of this motor bank, what is the feeder conductor? It's not the conductor down here for the motor, it's not the conductor in here for the motor. It's the conductor, the main conductor that feeds our splitter, that feeds out to these individual motors. So that's what our conductor for the motor bank is. And to size it is really fairly straightforward. All we really need to do is, if the motors are all continuous duty, it's really straightforward. And when you look at these motors, one's an auto transformer start motor, one's a full voltage start motor, one's a wound rotor motor. And we know that they are continuous duty motors because it doesn't say anything about any kind of duty cycle that these motors have. There's no intermittent duty 10-minute cycle, no periodic duty 15-minute cycle, none of that. And if we don't have any of that for these motors, we know they're continuous duty motors. So the conductor size, I should say feeder conductor size, all we do is figure out which motor has the largest full load current and go from there. So because these motors are on a 230 volt 60 hertz supply and we're not given the full load currents for them, we need to use table 44 to find the full load currents of these motors. And when you look in table 44 under 230 volt three-phase motors, you will see that the 20 horsepower motor has a full load current of 54 amps. The 15 horsepower motor has a full load current of 42 amps. And the 25 horsepower motor has a full load current of 68 amps. So we get those currents from table 44. And from there, to find the feeder conductor size, I simply take the largest full load current for any of the motors that I have, multiply it by 125%. So 68 amps times 125% or 1.25 plus the full load currents of the other motors that are on the bank. So plus 42 amps plus 54 amps, and that gives me an ampacity for this conductor. It should be about 181 amps. That number should come out to. And from there, we go to table 2 to size our conductor. Now, one thing to remember too is ordinarily we'll be given a termination temperature for this question. A lot of times it's 75 degrees, our equipment termination temperature. In this example, we're not given an equipment termination temperature. Rule 4006 states, where the termination temperature for equipment is not marked, the termination temperature shall be considered to be 60 degrees for equipment rated not more than 100 amps. So neither of these motors are rated for over 100 amps. That means we would use a 60-degree column from table 2. 181 amps would be a 4-aught conductor. So that's the size of our feeder conductor that feeds this group of motors, and that is pretty straightforward to do. All right. The second part of this motor bank is to size the feeder overcurrent device for the bank. And it's a little bit trickier to do. And what you start with is we take a look. If we're going to size the feeder overcurrent device for this motor bank, we're talking about this main overcurrent device here that protects the feeder that feeds all the motors. And what the code rule states is that if the main overcurrent device is a breaker, I want to determine the largest maximum breaker allowed for the single motor in the group based on the full load currents of the motor. So I need to know which one of these motors will require the largest breaker. A couple of them are fed by fuses, but that's not really important. What I want to know is what would each of these motors take for a breaker. I'm going to take that largest, the breaker calculation for the largest motor, and just add the full load currents of the other motors to it. Okay, when we look at these motors, to figure out our breaker size for each motor, we use table 29. For the 20 horsepower auto transformer start, if you look on table 29, you will see that auto transformer starting is listed partway down the table. In this, it says not more than 30 amps or more than 30 amps. This motor is more than 30 amps. So to size it for a circuit breaker, I would take 200% of this current. So for my overcurrent device, so for my 20 horsepower motor, to size that motor for a breaker, it is 200% of 54 amps, which equals 108 amps. For the 15 horsepower motor, to size it for a breaker, it is a full voltage start motor. On table 29, if I look under full voltage start for breaker, it's 250%. So 250% of 42 amps is 105 amps. And for the 25 horsepower wound rotor motor, to size a breaker for it, on table 29, a wound rotor motor, the percentage we use is 150%. So 150% times 68 amps equals 102 amps. So even though the wound rotor motor is a bigger horsepower motor than the other two motors, it is not the largest motor when we look at breaker size for each of these motors. Looking at breaker size for each of these motors, the auto transformer motor has the largest breaker size for a calculation. And so we take that largest calculation, we just take that largest calculated size for a breaker and add the full load currents of the other motors to it. So we're going to take 108 amps. That's for the auto transformer start motor, and we're just going to add the full load currents of the other two motors to it. So it'll be 108 plus 42 plus 68. And the number that we are going to get from that is 218 amps. That's the ampacity that we're going to use to size our breaker for this motor bank. Now all we have to do is use table 13, which is our standard ratings of breakers and fuses. And just go now. Table 13 is going to give us the size that we want. So in table 13, we want to select a fuse that has a rating not greater than this 218 amps. We can't exceed that maximum. So looking at the standard settings permitted, we have 200 amps, 225 amps, 175 amps, and so 218 is over 200, but not over 225. So we cannot go to 225. We have to go the next size down, which is a 200 amp breaker to protect that feeder overcurrent device. So that's how you size the breaker and conductor for a motor bank. They're fairly straightforward, and the module exam will give you lots of practice doing this because it's just full of different kinds of motor banks to give you practice finding these values, and it probably gives you some review for individual motors as well. Hope that helps.